So over the past few days, we've looked at how to find equations of tangents, normals, chords, so different types of lines that are to do with the parabola. So the last bit then really is using those things to prove different properties and theorems about a parabola. So let's have a look at one. Now, we talked a little bit about focal chords already. That's a chord, of course, that passes through the focus. We're going to prove that the tangents from the extremities of a focal chord intersect at right angles on the directrix. Now, the first thing I would do, it's a focal chord question. If they haven't already asked me to do it, I'm probably going to prove PQ equals -1, because I'm probably going to use that relationship in the problem somewhere. I mean, that pretty much is the key thing about a focal chord, that the parameters will multiply together to equal -1. One of the other things we saw when we were doing our different proofs and that was the slope of a tangent always turned out to be the parameter. So the slope of the tangent at P was little p, slope of the tangent at Q is little q. Now if we combine those two ideas, what do we got? The slope of this tangent times the slope of this tangent is -1. What does that tell us about the two lines? Yeah, if the slopes multiply together to give -1, the two lines must be perpendicular. And so there's the intersect at right angles. Okay, so we've combined a couple of the ideas that we've looked at to work out, okay, they're going to intersect at right angles. Now the other thing is on the directrix. One of the other things we did was we found the point of intersection of the two tangents. And that was this AP plus Q, APQ. We want to show it meets on the directrix. The directrix, what was the equation for the directrix? Yeah. So y equals -a. Well, let's have a look at the y value. The y value of this point in this intersection at the moment is APQ. But again, if we combine that with the idea back in part 1, PQ equals -1. So we say, well, look, yep, we know the y value is APQ. But because this is a focal chord, PQ is -1. So I get y equals -a, which is the equation of the directrix. So the tangents, therefore, do meet on that wonderful line of the directrix. So we can combine some of the things we've seen already. And that's, I guess, probably one of the classic questions about focal chords, proving that those tangents meet at right angles or proving they meet on the directrix. Okay. Reflection property. This is always a mouthful, this one. A line parallel to the axis of the parabola is reflected towards the focus, and any line from the focus of the parabola is reflected parallel to the axis. Thus a line and its reflection are equally inclined to the normal as well as to the tangent. What on earth does that all mean? It's a really fancy way of saying that the parabola satisfies the basic idea of reflection, which is angle of incidence equals angle of reflection. Remember that, don't you? That's basically what it's saying. So let's just show you what I mean. So here's a parabola, and what it's saying is any light ray or radio wave or whatever it happens to be comes in, it will bounce and end up passing through the focus. And the reverse is also true, that any ray that comes out of the focus will hit the parabola, bounce, and go parallel to the axis of the parabola. And that's why headlights of cars, I don't know whether you notice this, I mean, when you look at them, they look like they're circles. But if you look at a headlight of a car more closely, it's actually a parabolic reflector. And the reason it does that is the bulb sits at the focus of the parabola. And so what happens is all the light is sent out from the bulb, but it hits the parabola. And by this rule, every light ray then must be parallel to the axis. So it sends all the light straight ahead. Because if you're in a car, you don't really care if the light goes to the side. You don't need to know what's at the side. You need to know what's in front of you. And so that's why they use parabolas for headlights. So it collects all the light and pushes them forward. So if this is true, I should be able to show that the angle of incidence is equal to the angle of reflection. So what I'm going to prove is angle SPK is the same as CPB. Now the angle of incidence and the angle of reflection, and those of you who do physics could probably confirm this, is actually the angle it makes with the normal, not the tangent. But because the normal is perpendicular to the tangent, I can easily just show it's CPB and SPQ, because they're both going to be 90 minus that angle. So it is good enough to show the angle with the tangents are equal. And that's what I'm going to try and do. So I'm going to prove angle of incidence is equal to angle of reflection. So CP is going to be parallel to the y-axis, if this is going to be true, because we want all those light rays, bang, we want them to go forward. So the first thing I would do in this proof, and I'm not going to do it again because we've done it several times, but I could go and show the equation of that tangent at P is y equals px minus ap squared. Now from there I can say, well, okay, I can work out the coordinates of k. It's going to meet the y-axis when x equals 0. So I know the coordinates become 0 minus ap squared. So the length from S to K, well, we know from the axis down to K is ap squared. And then there's A above the axis to the focus. So the overall distance must be A plus ap squared. If that wasn't immediately obvious, you could, of course, use a distance formula and prove that. But as it's a vertical distance, I can just go, oh, it's that amount plus that amount. Okay. Now I'm going to find the distance from the focus to the point of contact, that point P. This one I've got to use the distance formula for. So it'll be 2ap minus 0 all squared plus ap squared minus a all squared. And expanding out, collecting terms, it actually turns out to be a p squared plus 1, which is that same distance. So yes, it does equal SK. So why did I do that? Well, that now proves that triangle, SPK, now it's on the previous slide, but you've got it in front of you there. If you have a look at triangle SPK, that's now an isosceles triangle. So we've got two equal sides. Well, therefore, SPK is the same as SKP. They will be the base angles or the equal angles of an isosceles triangle. But now that I've put in that parallel line, remember the ray that's going forward, SKP is also the same as CPB, because they'll turn out to be corresponding angles on the parallel lines. So therefore, and that's what I was trying to prove, SPK is in fact the same size as CPB. That's just one way of proving the reflection property. There's other ways, and I think our exercise actually does it a few ways. But there you go. So now next time you're sitting in the car and at night, you can just look at the headlights pointing forwards, seeing no light going off to the side, and you'll go, I know why that's happening. And anyone else in the car will go, really? You know why? You go, yes, I do. Yes, I do. And they'll be amazed.